In this video, we'll discuss electron withdrawing and electron donating groups on an aromatic ring. So if we have an aromatic ring, oftentimes there's going to be one or more groups on it, and we can categorize those groups into two main categories. They could be electron withdrawing groups, so those that pull electron density out of the ring, or they could be electron donating groups, those that push electron density into the ring. And whether electron density is being pulled out or pushed in has a lot to do with the reactivity of that specific ring and where other groups that are introduced will end up on the ring relative to our X group. So we'll start with electron donating groups. And electron donating groups are groups that can push electron density into the ring. So one example, this squiggly just being coming off of a ring, would be an oxygen. It has two lone pairs of electrons that it can push into the ring. A nitrogen has that one lone pair. And then if we had a carbon, that could push electron density into the ring through induction. So it would be through the sigma framework, not through resonance. But it's still pushing electron density away from itself. In all these cases, R is equal to either H or another carbon, an alkyl group. So any OR, NR2, or CR3 coming off of an aromatic ring is going to be an electron donating group, and it will push electron density into the ring. So we'll look at an example here. We can start with this guy. So we'll have a methoxy group on there. That's an oxygen with a CH3 coming off of it. This has two lone pairs of electrons. Those electrons can push down and kick the pi electrons that are next to them out onto the ring as a lone pair of electrons. So now I have a positively charged oxygen and a negatively charged carbon. My overall charge is neutral, though, just like my beginning structure. Once in the ring, this lone pair can get kicked around the ring. And now it can go here. So what ends up happening is electron density is pushed into the ring. So I have these three negative charges inside the ring, and overall the molecule has electron density at those three positions, and it's a more electron-rich ring. And so that being more electron-rich is going to dictate where other groups go and how reactive the ring is. On the other side, we would have electron withdrawing groups. And that will be any group that pulls electron density out of the ring. So any atom that has a partial positive or a positive charge on it would be an electron withdrawing group coming directly off the ring. So as an example, any derivative of a carbonyl compound is going to be an electron withdrawing group. We've got a partial positive charge on that carbon right there and a partial negative charge on that oxygen, and so those are going to pull electron density out of the ring, and so you could have a ketone, an aldehyde, an amide, a carboxylic acid, an ester. Any of those derivatives would be electron withdrawing. We could also have a cyano group. Again, we've got a partial positive on this carbon, a partial negative on that nitrogen. Or via just induction, we could have a carbon that has electronegative atoms on it, so CX3, where X is going to be a halogen. And actually then just the halogens themselves are also electron withdrawing groups because they're fairly electronegative, and so they pull electron density towards themselves. These bottom two would be via induction, so just pulling electron density out of the ring towards themselves. Via induction, the top two, you would have resonance contributors due to those pi electrons that are available. So if we look at an example of an electron withdrawing group, we can start with just a ketone right here. So these electrons can push up onto the oxygen. giving me this charge-separated species. So now I have a positive charge adjacent to the ring, so these electrons can fold in to make a double bond there. That gives me a positive charge in the ring, and once I'm in the ring, I can go around the ring. So the overall character of this molecule is that I have partial positive charges at these positions. So electron density is being pulled out of the ring is less electron rich, and that again will dictate where other groups that I introduce go onto the ring relative to that electron withdrawing group, and how reactive the ring is because it has less electron density in it.